Good morning, everyone. First of all, I would like to thank the organization for the opportunity of showing our work here. My name is Fernando. Let me start to train with the point here. My name is Fernando. Me and Victor, a professor on the University of São Paulo, did some work on choice of priors on changepoint problems, and today we will talk to you about our results. So before getting to the math, I would like to explain how we came across this problem and why we choose the path that we effectively choose. Okay, so since 2005 in Brazil, if a company is not going so well and they're not going to pay their debts, there is an option for them to ask the court for an opportunity to negotiate their debts again, and if all goes well, they get a second chance of doing great on their markets. Okay, but what happens is in 2015, Brazil suffered from a crisis, an economic and political crisis, and the unemployment rates were higher, and the taxes were crazy, and all this economic stuff. And when we are analyzing the data on the data we collected on the process of negotiation, we find out that maybe the crisis had some effect, and we would like to measure if something about the negotiation, some certain outcomes of negotiation, are being affected by the crisis. Right? So this is our background. Going more deeply on the data we had, the problem we were trying to solve goes pretty much like translating those kind of images that basically translates how a sequence of zeros and ones and success and failures changes through time, and we'd like to compare those figures to an evidence measure of how far is this pattern to a pattern where there is no change point at all caused by the crisis. Okay, so in the left picture, we would like to have a high measure of support to no change point at all, and on the right figure, we would like to have a low measure of evidence of no change point because we have some deviation on large times. So here's the beginning, 2013, and here's the end of our period of collection. And at the end, probably because of the crisis, the number of successful negotiations became a bit lower, right? The last negotiations on the data set were less likely to result in a success. Okay, so with this problem in mind, we would like now to go down to the math and construct a model that help us to effectively build the measures of evidence we're looking for, right? So we will do that thinking about the observation of a sequence of zeros and ones, and in our minds, we will try to check if if you see that sequence as the results of coin tosses, we would like to, in our heads, check if someone changes the coins that they were flipping, right? And in this framework, we need only three parameters to translate this problem to a mathematical setting. We need tau, the point in which the coins are swapped, the flip that changed it all, and two pair of probabilities that measures the distribution that we are estimating on both sizes of the time series. Okay. So this model is a very famous model, and on the literature it has appeared in two ways that I'll explain you briefly, because I will explain them to you briefly because they have some difference on the form to define the parameter space that might change how we construct our measures. Okay. So the prior is pretty much the same on the two models that we will describe. You define a prior on tau, and then conditional on tau, you define a prior on the probabilities. That is pretty much a density on the unit square. The first model dates back to Hinckley in the 70s, and they assume that there are two coins being flipped. You effectively observe the results of two coins. So if you need to express the hypothesis of no change point, you need to look to the parameter point in which the probabilities are equal. Okay. So there is no point that relates to only one coin. Only one coin was flipped. There is only point that tells you the two coins have the same probability of head. So there's no change because the coins are essentially the same. This is important because when you do that definition, the change point hypothesis is a new measure set. So you need to, if you want to test this hypothesis on a Bayesian setting, you would have to construct a base factor or something, and you should keep that in mind, right? The second formulation is a more recent formulation that is basically equivalent to giving mass to the parameter point in which the probabilities are equal. Right? First, the main difference is that now you introduce you can have tau equals 1 because you can have tau equals 1. So the points that relate to the no change point hypothesis now includes this set that by your prior definition has a positive measure. So here you can test this hypothesis on a Bayesian way without thinking about giving a measure just to make the test, okay? Because it's already on the prior definition. The both models go the same on likelihood and posterior inference. At the left of tau, you have one binomial. At the right of tau, you have another binomial. And the posterior inference is pretty much vanilla, okay? You integrate all the parameters you don't want, and you can condition you condition on tau because tau has a discrete distribution and the probabilities have a density and everything just works, right? You don't need to think much about it. But even though the posterior, the interpretation of the model is quite simple, and the posterior inference is quite vanilla, there are some irregularities on the model that are not so much mentioned usually, right? There are some properties that when you come across these properties on any statistical model, you became very, very frightened, right? But here, people usually don't talk about them. First of all, the model are non-identifiable. You have lots of parameter points that gives you the same measure on the sample space. So you should expect that it's hard to effectively learn the parameter that are generating our data, okay? The second thing is that the parameter space grows with the sample size. And this is not common at all, right? And it kind of gives you a flavor of a non-parametric problem because the sample size is growing, so maybe you might be going to an infinite dimensional space, right? Of course, this is not what is really happening, but you might think about it if you in a statistics way. So okay, now let's get down to the hypothesis testing after the background. Because of what I told you, that the second model is like giving mass to the null hypothesis of a base factor test, I will use only the second model, and my main tool to check if my hypothesis is true or not is use the posterior probability, right? So our test statistic will be the posterior probability of tau equals 1, okay? Using that on the data we had to test our hypothesis, what happened was really surprising, because this picture that tells me how the probability of approval negotiations by the court grows in time kind of tells me that there's no change at all, right? The red dashed line is how how it should grow if there is no change point. It's pretty much close of the data. And even though with the posterior probability calculated is only 2%, right? That's kind of surprising because I'm a Bayesian, and I would like that my Bayesian computations mimic what my head do when I see a picture, right? So why is this such a low number, right? Thinking about that, we choose to try to understand what is happening, thinking about consistency. If a Bayesian model is consistent, you think about a true parameter value, and your Bayesian model will, of course, learn this parameter value on an infinite sample. Okay. Yeah, I'm not so Bayesian because I'm thinking about true parameter priors and true probability measures, and nothing of that really exists. But I really would like that my model has this property. Okay. But then we prove a theorem that kind of let us down, okay? Because we prove a theorem that we call the Stubber-Bayesian theorem, and he pretty much states that if you're prior on tau, if you have uniform priors on the probabilities on the probability of heads, and you have a prior of tau that with n makes this ratio grows to infinity, your probability of tau equals 1 goes to 0 for every probability of heads under no change point. Okay. So what this is telling us, it's some Bayesians, even with infinite data, won't learn that they are observing no change point at all. Okay. So that's pretty strange, okay? Because I don't want my model to do that. So I will never choose priors that do this. And oh, of course, and my model was one of these, okay? I choose an uniform prior for tau, and when you do that, the ratio that I mentioned on the next slide behaves almost approximately like a log, and it diverges, okay? So I have a problem there. This is pretty much what the theorem is saying, okay? For every true probability of heads under a no change point hypothesis, your posterior null probability goes to 0 quite fast. Yeah, so now that we know that we have a problem, we would like to think how we solve this problem. And we find out that it's possible to fix this problem with a similar idea that we used to prove the Stubber-Bayesian theorem. If the same ratio goes to 0, then you have under the null hypothesis, the probability of no change point at all goes to 0. So, okay, as a Bayesian, would like to be on the theme of the reasonable Bayesian, right? So I would like to choose priors that satisfy this property. Okay. Although this might seem quite strange for a full subjective Bayesian, because I'm telling you that you not choose the prior that translates your beliefs to a mathematical point of view. I'm telling you that some priors are idiots. Okay, so we would like to find another way to solve this problem. Okay, and effectively, there is another way of solving the problem. Two men who are here today wrote a paper in the final years of the last century, describing a measure of evidence that kind of counts the number of points in the parameter space that are less likely than the most likely point in some hypothesis. Okay, and this is a number that goes from 1 to 0, and it measures the agreement of your posterior to a certain parametric subset of the parametric space. Okay. If you use this, is a number from 1 to 0, and it measures support. So if this number is small, I should reject my hypothesis, and if this number is large, well, the data support my hypothesis. Okay. Why I'm telling you this? Because using this measure of evidence, you would expect then an inconsistency in the sense of this measure of evidence would be if under the null hypothesis this number is typically 0, right? Or it goes to 0 with the sample size. But that is not the case. This is a simulation we've done, and if this we use the probability of heads is equal 0.6 or something. Here what happens is that the evidence concentrates in a point that's far from 0, right? We don't have the behavior that we had on the base factor. So, knowing this distribution, we can construct tests of level alpha and classical statistical stuff, and we have the security that we will not do some inconsistent decision on the end. So, getting down to the conclusions, I summarize my talk in 3 points. The first one is, in changepoint models, some priors lead to inconsistency. So if you use a changepoint model in your life, you should be aware of that, and you should be careful, because those models are highly irregular, as I told you before. The second point is that if you're doing a binomial changepoint problem, I already solved the problem for you. You just really need on this ratio that depends on your prior, that depends on the sample size, and it will help you to choose a prior that is consistent, if you care about that. If you don't care, okay. The third conclusion, and last one, is that if you don't care about consistency, you still can have, if you care about consistency, but you don't want to give up some priors for achieving consistency, you can use the full Bayesian significance test, because empirically it seems to work just fine, okay, even though the model is highly irregular. This is what I had to talk to you today. Thank you for the attention.